you will also be available at one or the other coffee break. And we move on to our final speaker in this session. So Rim, are you there?
I'm here. Did you hear me?
Nice. So could you please share your screen again?
Yes. Just 1 minute. Did you see my screen?
Yes, we can see your screen now. It's not full screen mode yet.
Control plus L.
Yeah. Okay. Thank you.
The short key is Control plus.
Very nice. Thank you. The student volunteers are so nice and helpful here. Thank you so much. Okay, so yeah, it is my pleasure to introduce the last speaker in this section, which is who's Rim Saddem. And if I got it correctly, you received your PhD from the Université de Montpellier in 2018 and are now a postdoc at the French Institute of Science and Technology for Transport Development and Networks. And I'm looking forward to your talk. So the stage is yours.
Thank you for the introduction. So I am Rim Saddem, a postdoc at IPSAR laboratory, and the work presented here was performed when I was a postdoc at the Semantics laboratory. Let's start by the context. So a business process is a set of activities organized to achieve a goal, and a business process model and notation is the standard notation for modeling a business process. It includes a rich set of constructs for control flow, inter-process communication, and time-related concerns. However, spatial concerns are left apart while being essential to several application domains. Let us consider, for example, the domain of robotics agriculture. So here we have a set of robots, and we have different variants of the environment. Fields are linked by roads, which are used for the mobility of robots, and here we have a river with a bridge that can be one way or two ways. So the environment may have an effect on the process of the robot. For example, if a field is planted, then the planter cannot fit in together. And if the robot cannot take, for example, the bridge in the forbidden sands. And in the other side, the planter or the robot in general have an effect in the environment. For example, if a field is not planted, then the planter planted, and in this way it becomes planted. If you want to represent the model of the process using the business process, there are two approaches. The first one is to use variables, and in this case, we will explore quickly. The second is to use abstraction, and in this way, we will have the following business process. Down here, the process starts, then it checks if there is a field to plant. As we can see here, we use a textual description which is supported by sBPMN. And indefinitely, the process either select to move to the field and plant it, or it selects to undo. And if we want to implement this process in the semantics, we will have an infinite execution trace, and we can avoid that by using, for example, criteria of liveness, but for us it is not a pertinent solution. So what we propose? We propose to extend the BPMN with a real representation of the environment and not only an abstraction of it. So this will be done using the space structure. Then we propose to define exactly the reason of branch selection. And for that, we will use a formula. As example, here we have a formula reachable and to plan. And the evaluation of this formula is stored in a variable that we call Z. And we want to express the robot mobility, and this will be done using the robot mobility, the action move. And finally, we want to represent the effect of the robot action in the environment, and this will be done using the action update. As you can see here, the default sequence flow, it's only triggered if the formula is not verified. So, in the rest of the presentation, I will talk about the different steps that we follow in order to verify a business process. And the first step, we will talk about the BPMN syntax extension, and we will talk about the space structure, the space formula, and the space actions, which are move and update. Then we will talk about the BPMN semantic extension, and I will conclude by addressing the verification. So let's start with the space structure. In space structure, we need to model the different individual location of the environment. So, and where a process can be located, and this is supported using the element B, which is the set of base location. Then sometimes you need to group base location in a category, and then we can apply, for example, condition in this group. And for example, if we take the group location to plant, it presented all fields in the environment which are not yet planted. And finally, we need to represent the possible move between base location, and this is considered in the element transition. Now let's move to the space formula. Space formula are used to denote a subset of base location, and they are used both in conditional sequence flow and in mobility action. The space formula is generated by using formulas, and we add a variable, a base location, a group location, and the formula here, which means the current location of the process, and the formula reachable, which denotes all the reachable base location from the location of the process. There, for example, we have the formula to plant, which represents all not planted fields, and the formula reachable, which is from F4 to F6, because the base of the process in F4, and the reachability and the reachable and to plant formula is the intersection between these two subsets of base location. So for space action, if you remember, we have two space actions which are moved for mobility, to represent the mobility of the robot, and the syntax is the move F, which denotes that the process moves to a location satisfying F, and we have the action update, which denotes the update of the environment by removing the value of U from J minus and adding them to J plus. And we also add the action pass, which is not related to spatial content. Now we will see the example SOO. We will see the example SOO6, and the green box are BPMN element extended, and the blue text, it represents the extension text. So let's consider, let's explain this model. We have a planter and we have a controller. The controller started by activating the planter, and in this case, the planter will start the engine and wait to receive a direction. Then the controller checks if there is some zone without crop, and these done using the formula N to plant. To plant is the set of all not planted fields, and any is a kind that select just one base location belongs to this group, and it stores this location selected in the variable ZNC. Then it sends a direct message to the planter. The planter will try to reach this location selected, which is ZNC. If this location is reachable, then it will move to the zone planted. Then it sends an acknowledgement message to the controller, which will update the zone information by removing the value of ZNC from the to plant and adding it to planted and to water groups. And in the case that the selected zone is not reachable, the planter will send an error message to the controller, which will deactivate the planter. And finally, the planter will try to reach the base. And if it is possible, it will go back to the base and stop the engine. And in this way, it will end at the base. Otherwise, it will stop the engine. And in this case, it will end in the fields. So if we want to explain the semantics of the extended element of the PMN, the semantics is based on the notion of states, and we use a token-based approach which follows the semi-formal semantics of the standard. So a state is defined by node marking, edge marking, and the space configuration. And what we mean by space configuration is a couple of substitutions. The sigma is a variable substitution which assigned to each variable a base location. And we have subs that represent the substitution from each group location to a set of base location. Now, the semantic is organized is a set of rules describing how token from moves around node and edge, and in order to form the complete execution. And we define two predicates. The predicates start enabling the node to start its execution, and the predicate complete enabling the node to complete its execution. Now we will move to the XOR semantics, and which is to XOR semantics. And in this semantics, the third step is to select all conditional sequence flow where the formula is satisfied, and this is taken here. Then we need to choose only the conditional sequence flow where the condition is true, and for that we need to define an order of conditional sequence flow, and this is taken in this part. And finally, we need to update the variable, and depending on the condition kind, all or any, either we will select a single location from the formula interpretation, or we will use select all location. And now, our first order logic semantics is implemented in the Laplace theory. We have a Laplace representation of our sBPMN model, and we have a set of generic properties and user-specific properties. We use the TLC model checker to perform verification, and in the case that a property is not verified, we have a counterexample that we can animate using our tools, which is open source and free. So here we have our model S006, And we have some variant of this model. The S007 here, we suppose that the update will be performed in the planter process. And here we have the full models with a sprayer, the planter, and here the controller will control both robots. And finally, we have the model S009 where we add a group location that we call not treated, and if the zone is not reachable, in this case, we will add it to this group. If we look now in the verification results, we can, here the three first properties are generic properties, and the properties 4 and 5 are user-specific properties. For example, we can, for the property 4, we can say if the planter always ends in the bin, and we can see that this property was not checked because the bridge is one way and the robot cannot return to the base. And the property number 5, which is to plant always and empty, it is possible because in this configuration of the space structure, it is possible to plant all fields. Now we will move to this the second context where the base is located in F4, and in this case the planter always ends in the base. This property was checked because in this configuration it is possible to reach the base, and if to plant always ends empty, this property was not verified because the bridge is one way. So for the conclusion, we have extended the syntax of sBPMN. We have then extended the semantics in the first order logic. We have implemented our semantics in Laplace theory. We have user and generic properties, and we have a counterexample animation, and our approach is supported by a tool which is free and open source. As perspective, we propose to evaluate our approach in more examples, and we propose also that the actions of process may modify the possible moves. And now, for example, location is shared between process using variables which have a global scope. We propose that this information will be shared using the Mrs. payload. And finally, we propose to study in the future work the interplay between time and space. Thank you.
Thank you very much for this very nice talk. Thank you. Yeah, I think we have a few minutes time for questions. Again, you can ask them in the chat or raise your hand if you want to ask a question. So maybe I can start with my questions. It is very nice work. I like that very much. In particular, in one project, we are looking at resilient supply chains now, and I think a spatial extension to sBPMN can really help us there. I was wondering, I really like how you kind of separate the concerns of the spatial concerns from the rest of the system, but what does it mean for the verification? Can you elaborate a bit on how the verification is affected, for example, by more complex spatial models, or if you replace this spatial context, what happens there?
For example, here for the verification, if we change the context, for example, if here we suppose that our robot is located in this field, so we can see that some properties which was not checked here became checked because we only modify the context of the robot where we only modify the environment where the robot can be located, and also the model of the process here will not be changed. Only the structure will be changed, and we will have a generic approach for different environment. We can check different environments using the same process, and we can use, for example, the same space structure for different models process.
Okay, I see. Yeah, great work. Thank you very much. If there are no more urgent questions on this, we also have the second speaker who we missed due to an emergency here now. So if there are more questions to Khushrai Madnani, whose video we have watched about the generalizing the non-functionality for time temporal logic with freeze quantifiers. So you can ask questions to Rim still or to Khushrai. Maybe right now, if you have something urgent, you can just raise your hand. And if we have no questions right now, I just would ask speakers to please go to WonderMe for the now following coffee break, and then maybe people can come up to you in particular. To Khushrai, there might be more questions waiting for you, but people might have rolled back to your talk. So yeah, thank you, Juan. Just shared the WonderMe link in the chat. Yeah, and maybe you can go there and be there for questions. And the main conference continues at 6 with the session on program verification. And yeah, with that, I'd like to thank the speakers again for the nice talks we had in this session. And yeah, see you later. See you again. Thank you.